Okay, we were looking at exponential functions in 5.1 and 5.2, and now we're going to be looking at logarithmic functions. In 5.1 and 5.2, we were looking at bases where either our base was between 0 and 1 or our base was greater than 1. And we're going to be focusing on bases that are just greater than 1. And recall, if our base is greater than 1, then our graph should be something that is just increasing as we go from left to right. And we know anything raised to the 0 power is 1, and we have this y-intercept at 0, 1. So if we come down, let's look actually down here at our green graph. Here would be a graph of an exponential where our base is greater than 1. And recall, if our base is greater than 1, our domain for our exponential of y equals b to the x, our domain is all of our numbers, all real numbers, negative infinity to infinity. Our range are our positive numbers from 0 to infinity, not including our 0. Our y-intercept, well, we know anything raised to 0 is going to give us 1, so our y-intercept is that point 0, 1. We know we do not have any x-intercepts because our quantity will never equal 0. And with our exponentials, recall we had a horizontal asymptote at y equal to 0, this x-axis. Right? We had this horizontal asymptote that our graph was approaching as x is going towards a negative infinity. Our graph is flattening out. The quantity is getting closer and closer to that value of 0, but it's not going to actually equal 0. So with this green graph, with this exponential graph, we know it's a function, passes the vertical line test, but it also passes the horizontal line test. We could draw a horizontal line anywhere through that green graph, that exponential, and it does pass that, which means that our exponential function is a one-to-one function. And recall that if it's a one-to-one function, that means then that an inverse has to exist for that exponential function. And our inverse, recall, is always reflected over that line of y equals x. And any xy points that were on our function, the yx points, would be on the inverse. And so if we just flip that green graph, that exponential, over that line y equals x, we would get this blue graph over here, that reflected graph over that diagonal of y equals x. And this point 0, 1 that was on our exponential, we know the point that 1, 0 would be on this inverse graph, this reflected graph over the line y equals x. And recall, to find the equation for our inverse, well, if our exponential was y equals b to the x, then to find the inverse, we know we just switch our x and our y variables. X's become y's, y's become x's. So initially, our inverse equation would just be x equals b to the y. But we know we don't like to leave equations in the x equals form. We always want to solve for y. So instead of leaving it as x equals b to the y, our final equation would be y equals log x base b. So our logarithmic functions are just inverses of our exponential functions. And if we look at some information about our graph here, our domain for our log graph, or we call our domain, our x's, are just going to be what was our range for our exponential function. Our domain, we can only have values of x that are greater than or equal to 0 because our x's are what our y's were. And our range is whatever was our domain for our exponential function, which means our range is everything, which we can see in our picture. Our x-intercept we can see in our graph was the point 1, 0, which should make sense because we had a y-intercept of 0, 1 on our exponential. Our y-intercept is not going to exist. We are not going to hit the y-axis at all. And instead of having a horizontal asymptote, this equation of y equals 0, our logarithmic functions are going to have a vertical asymptote at x equal to 0. So we have this vertical line for our logarithmic functions that our graph is going to get very close to, but it is not going to cross over. Okay. If we continue with that same thought process, and recall that we were looking at bases of e was just a number, right? It was just this 2.71 approximately. So our green graph here is just our graph of y equals e to the x, that 2.7 to the x. We've got that y-intercept here at 0, 1. And recall with our y equals e to the x, our domain was everything. Our range was just values that were above 0. We did not have an x-intercept, did not exist because we know that our exponential graphs are never going to cross that x-axis. We have that y-intercept at 0, 1, and we have that horizontal asymptote at y equal to 0 as our x values are going towards a negative infinity. That graph is getting closer and closer to that x-axis. And we know that that graph of y equals e to the x does pass the horizontal line test, which means it is a one-to-one function, which means an inverse function exists. And whatever x, y points were on this y equals e to the x, we know that the yx points are going to be on the inverse function, which is reflected over that line y equals x. And we have this point 1, 0, which we know definitely would be on that inverse function. So if y equals e to the x was our exponential function, the inverse, if we switch x and y, then the inverse is just this equation of x equals e to the y. But we don't like to leave equations as x equals. We want our equations to be written as y equals. So if we rewrite it with y equals, then our equation is y equals the log of x base e. Now base e is such a popular number. Okay? It's a very common number, especially in calculus, that log actually gets its own special name if you're working with base e, a base of approximately 2.71. So instead of using log, whenever we have a base e, a base of 2.71, we're actually going to use ln, which actually is natural log because e is what is referred to as nature's number. It is so common that it shows up in so many different scenarios that ln or natural log just refers to when you're working with a base e, a base of 2.71. And if we look back at this blue graph, our log graph, similar to what we just looked at if we just looked at a general base, again, we know that our domain has to be something that is greater than 0. You cannot take logs of anything negative or 0. It always has to be of positive quantity, something greater than 0. Your range is negative infinity to infinity. You'll get everything out. You have that x-intercept at 1. Y-intercept does not exist. You will never cross that y-axis with your basic log graph. And you have that vertical asymptote at x equal to 0, that y-axis. That log graph is getting closer and closer to that y-axis, but it is actually never crossing that y-axis. So let's look at some of our log expressions. What are these log expressions? Okay. Well, if you're looking back real quick, when we were rewriting these equations, when we switched our inverses, x equals b to the y, and we said we don't want to leave our equations like that. That y was just in the exponent position. And so all y is, this expression is just a way of representing that exponent. So anytime you're working with logs, you're just working with exponents. X equals e to the y equals the log of x base c, or natural log of x. Again, just ways of representing that exponent. So anytime you're evaluating these log expressions, all we're doing is just looking at a way of expressing the exponent. It's just a way to represent that exponent. So if we look at number 1 here, the log of 4 base 2. Log of 4 base 2 represents an exponent. So what exponent, if we take base 2, what exponent do we have to raise it to in order to get 4? This expression is equal to some exponent. So 2 raised to what exponent gives us 4? Well, we know that 4 is 2 squared, so that exponent is 2. Or the log of 4 base 2 is just equal to the number 2. Okay. We look at number 2. Log of 9 base 3. Well, this is just representing some exponent. You are solving for the exponent. So if you take base 3, what exponent do you have to raise it to get the number 9? And we know that 9 is the same thing as 3 squared. And so that exponent that we would have to raise 3 to is just the number 2. So the log of 9 base 3 is equal to the number 2. On number 3, most popular bases are e, which if we use base e, you're going to see ln, and base 10. And since base 10 is very popular, if you see no base written, on number 3, we have no base written, there is a 10 that is implied. So on number 3, this is asking the log of 1/1000th base 10 implied. Again, logs are just ways of representing an exponent. You're solving for that exponent. So if we take base 10, which was implied, what exponent do we have to raise it to get 1/1000th? And we know 1/1000th is the same thing as 10 to the negative 3. So the exponent is a negative 3, or the log of 1/1000th base 10 is equal to a negative 3. If we jump down to number 6. On number 6, again, logs are just ways of expressing exponents. So the log of the square root of 6 base 6 is equal to what exponent? If we take base 6, what exponent do we have to raise it to get the square root of 6? Well, we know that the square root of 6 is just 6 to the 1/2 power. Bases are the same, our exponents are equal, so we know that the log of the square root of 6 base 6 is just equal to the number 1/2. Okay. Let's jump down to number 7. The log of the 5th root of 16 base 2. So 2 raised to what exponent gives us the 5th root of 16? If our base is 2, we want to try to rewrite our quantity if we can with a base 2. Well, the 5th root of 16 is the same thing as 16 to the 1/5 power. And since we have a base 2 on the left, well, 16 is the same thing as 2 to the 4th power to the 1/5. And power to power, we know we multiply, so that's really 2 to the 4/5. So 2 to what exponent gives us 2 to the 4/5. Once our bases are the same, we know the exponents have to be equal. This is just equal to the number 4/5. Okay. Leave a couple of these for you guys to practice. On number 9, the natural log of e to the 8th. Anytime it's natural log, that means base e is implied. So this is asking us, if you take base e, what exponent do you have to raise it to get e to the 8th? And we know if our bases are the same, our exponents have to be equal, and this is just equal to the number 8. On 10, natural log of the 6th root of e. Again, base e is implied. With ln, your base of e will not be written, it's implied. So this is asking us, if we take base e, what exponent do we have to raise it to get the 6th root of e? Well, we know the 6th root of e is the same thing as e to the 1/6 power. And so if our bases are the same, then our exponents have to be equal. So the natural log of the 6th root of e, base e, is equal to 1/6. Okay. If we jump down to 12, the log of 27, base 9. 9 raised to what exponent gives you 27? Well, in order to solve for the exponent, if you can get like bases, you want to try to do so. 9 and 27 both can be rewritten with base 3. 9 is 3 squared, and 27 is 3 cubed. And once our bases are the same, then we can set our exponents equal, which means that 2x would have to equal 3, or x is equal to 3/2. So the log of 27, base 9, is equal to 3/2. On 13, the natural log of 1. E raised to what exponent gives you 1? And we know that if you take any base and you raise it to 0, you are going to get 1. So the natural log of 1 is just equal to 0. On 15, the log of 1, base 10, is implied. 10 raised to what exponent gives you 1? Well, we know that if you take any base and you raise it to 0, you get 1. 10 to the 0 is the same thing as 1, so the log of 1, base 10, is equal to 0. So the log of 1, any base, is going to always equal 0. On 14, the natural log of e. Well, with natural log, base e is implied. So e raised to what exponent gives you e? And on the right, we have an exponent of 1 that is implied. And if our bases are the same, our exponents are equal, the natural log of e is just 1. On 16, very similar, except for base 10 is implied. But the log of 10 is just asking us, if you have a base 10, what exponent do you have to raise it to get 10? And we know an exponent of 1 on the right is implied. Bases are the same. Exponents are equal. The log of 10, base 10 implied, is also just equal to 1. So there's a few more there for you, 17, 18, 19, 20, 21, and 22. And I'm going to let you try those, and then we will come back and start